Welcome to the NERI SimCenter's Live Expert Tips. In this session, we introduce you to the Probabilistic Learning on Manifolds algorithm to create surrogate models of structural response prediction. The examples shown in this session will use this algorithm to learn an existing dataset and generate new realizations that preserve the data structure. A second example will increase the sample size of nonlinear time history analyses and learn the correlation between different structural response parameters under earthquake ground motions. Our expert today is Dr. Kuanshi Zhong. He is a postdoctoral research fellow at Stanford University. He received a PhD in civil and environmental engineering from Stanford and bachelor's of civil engineering from Tongji University. His research interests include the behavior and critical failure modes of reinforced concrete structures, surrogate modeling using statistical learning techniques, and methods for assessing and enhancing community resilience to multiple hazards. At the SimCenter, Kuanshi is the lead developer of the earthquake engineering with uncertainty quantification application. Kuanshi, thank you for being here.
Thank you, Matt, for the warm introduction. And yeah, it's my pleasure and a great honor here to share some of the latest developments in the earthquake engineering with uncertainty quantification tool in SimCenter. And so as you probably heard about the tool, the full name, and it's actually a combined or integrated platform to predict the response of building subject to earthquake events, and including uncertainty quantifications in the ground motion side, but also in the structure properties. And just to quickly flash through some of those useful links. If you have any interest or questions, please check out this link, but also feel free to get us back anytime or stop the through email or other our SimCenter form later will be introduced today. And today I will go through first about a brief introduction for the probabilistic learning on manifolds, short name PLoM, and its major algorithms and implementations in SimCenter tools. We have that in both PLoM and the EUQ, but today I will focus on the EUQ. And we'll have three examples. I just add one second example just to bridge through the first and the third one. So first one, we're looking into a simple spiral data structure, and just to show demonstrate the algorithm in the two. And then the second one is a bit more complex structure, but still simplified MDOF systems under earthquakes, and try to see how to incorporate the ground motion intensity in the data set generation and surrogate modeling. The last one is going to a 12-story more practical uses of this tool here. So so first about a little introduction to the method PLoM itself. So this method proposed by Dr. Sola and Dr. Garner initially maybe 10 years ago, but more getting to a big shape now in the past 5 years. So the key idea for the algorithm is that imagine that you have a well-defined problem. Unfortunately, the initial data set you could get either from the real world or from numerical simulation is limited. So basically a small sample problem, but it's hard to really get a stable or reliable estimate the statistic from that small sample. The PLoM method helps you to really learn the data structure from the small sample, regardless of the linear or nonlinear and the local structures, and help you to produce new data sample. In the meantime, preserve the important correlation structures in a computational efficient way. And this two, just to reference this two paper that well documents the methodology, and we actually follow this method to create our backend analysis script to implement these methods. And just a quick picture of the major algorithms that's involved in the PLoM. So there are 6 key steps. So I have also very little cartoon here for a quick example using this spiral data xy, x1, x2, x0, 3-dimension, and following some spiral rotationally increasing in z direction, and we'll have some noises in each dimension. And it will first do a very simple scaling to really normalize these things to 0 to 1 space. And then I will conduct a standard PCA. We'll map this to the full dimension without the reduction. The idea is that we will maintain that space, but send that entire data structure to kernel density estimation to get the parametric estimates of the distribution, joint distribution of the data. And after that, we'll construct a Markov chain Monte Carlo generator using the polynomial chaos expansion with the help of the Ito stochastic differential equation formulated for a dissipation Hamilton dynamic system, which will mount it on this non-parametric estimates of the probabilistic distribution. And after that, because it can be really high dimension once we look into a sample of the data. So we will also to do the dimension reduction to help us to identify where the data actually concentrated. For instance, in this example, we actually maybe only need some dimensions where the data will only concentrated in the simple spiral structure. So here we Dr. Soga and Dr. Garner actually utilized the diffusion maps, which help us to reduce the original dimension using a vector basis following a tolerance selection. And so following the tolerance, we will select only the first few vectors that really describe the data concentration, and then construct a reduced order stochastic differential equation, and then numerically solve that to compute new realizations and transform them back to the original space. And as you can see, this is just a, I plot just the 3 time steps so that we solve the differential equation. And you can see it's kind of like a describe well of the original data structure. And this example, I will also demo that later in a minute. So as for the implementation in the SimCenter 2, here just to show you a quick example for the user interface that we have. We have this new PLoM methods included under our UQ engine. And the UQ engine is one of multiple steps that's in the EUQ2, which bridges through from the data setup to the time to the results analysis results. And but in this example, we'll just look at first at the UQ uncertainty quantification tab here, and the PLoM model, and we'll have several different options for defining the input data sets. Here, first option is just to input to the data file. It can be input file and output file. For instance, your ground motion intensity measure is the input, and then the structural responses could be go into the outputs. And we provide the user interface, let you to choose the individual CSV files, and you can generate a new samples to expand this data by learning the local structure and preserve them. And the second option would be based on generating and simulating the initial data sets through the EUQ functionality, which will be introduced in a minute. That's the simulation panel and the FEM panel that will help us to first build a structure model, and will run a number of simulations using that analysis model, numerical model, to create the initial data sets, and then learning from that data set to create the surrogate model to continue. And for the EUQ, specifically, we also include a ground motion intensity measure calculator, so you can select the different options for your key ground motion characteristics that will be included automatically in the training step. So you don't need to really worry about to develop a new set of the data by manually calculating ground motion intensity from each individual records, which also are automated in this entire process. I will do this demo soon. So the first example today for just to quickly demo the algorithm itself, looking into a simple 3D spiral data set. And the initial data, input data, have about 200 data points, which simply generated from these three formulas here, x1 and 2. If you project them to the horizontal plane, would just be a circular data points with a radius of 10 and have noises. Just assign Gaussian noises for that, and in the vertical direction, just time step moving upwards. And in this case, I just want to generate new samples about 5 times more than the initial data points. And by this, I will just jump to our EUQ2 here. I will just open a new one here. So once you download and unzip this EUQ download zip file on Windows, of course, I have the Windows platform today, and you can directly click the EUQ executable to launch the user interface. And from there, and the first tab we have this looked into is the uncertainty quantification, and we pick up the SimCenter UQ engine and select the PLoM model under the drop-down list for SimCenter UQ method category. And from there, we arrive at the options for input data file or sampling the simulation. So here I will just keep ourselves in the raw data parts. And here I will just load the raw input data for the access. I will just have the example file here. To load it from the spiral data. So I split the data set to input and output here for this case. So I will just open these two files as well in a minute to show you the data structure there. So I input the X and the Y, which is the first one is the X1, and the input data Y, which I treated as the output, is the other 2 dimension. So you could see it's X1 is in this first input file, and the X2 and X3 are in the output file that loaded into the EUQ interface. And then I can just keep it the new sample data points. So in my input, I actually mentioned before, I have about 200 data points, and I want to generate 5 times more. And once it's set up, we can just click run here. And in the backend, the EUQ will call the PLoM algorithm to follow the major steps that we just briefly saw in a slide before, and to train this learning the data structure and generate new samples. And it may take a few seconds. It will give us, once it's completed, it will bring us to the REST panel. Please bear with me a few seconds here. We can also look into what happened actually in the backend. It's actually quite busy in the backend under the local work here to create this all the data structures here. You can see we actually mounted the 2 input file into one, and then start to get the surrogate model training parts. And I think it takes longer than I expected one day. Okay, so it's finished. And once it's done, it will first bring us to a summary picture here. Will tell us about the PCA, since we only have 3 dimensions, so it's kind of like 3 data points, the first, the second, and the third eigenvalue for them. But most interesting thing would be if you click on the data values. So this is the data table for all the new samples. If you scroll, I can just do a little bit more. So you can see all the numbers here. And if you scroll down, it's about 100 data points, the new sample. And As you can see, I just plot the x1 and x2 for each individual realizations here. X-axis is the realization number or round number we can call it, and the y-axis is my x1. And let me just quickly check if my x2 and x3 follows the same data structure, and actually see this projection on the horizontal space x2 and x3. It's kind of like a new generated samples that learned from the original structure have a circular data shape with uncertain little bit noises to have this bandwidth here. And also you could see that's kind of like a spiral. You could roughly tell this kind of like climbing up the spiral data structure here. So this is just one simple example to demonstrate that the idea how to incorporate the initial data set you already have, maybe from a simulation. Here I have just one simple example. I numerically generate those, analytical generate those things from the formula, but you can imagine that could be a data set you want to look into with from your experimental studies or numerical simulations. And the second example I would like to introduce today is using the generating a new sample for training sample first. Well, I will move back to this UQ tab here at the first tab. Instead of using the input data file, which the first example demoed, I will use the sampling and the simulation. And first, I will once define that, which means I need to define numerical model first. So in this example, let's move to the navigate to the same tab, structuring information model, which under which we have multiple options. You can use OpenSeas as your TICO file source file to build a new model, or use the still building model AutoSDA, which developed by Dr. Burton with his group, or recently concrete building. This all help you to build a structure and a numerical model. But in this example, just to keep it simple for demonstration purpose, MDOF system, 12-story, and have the yield displacement, yield drift ratio for each story identical, 1%, and the hardening ratio 5% after the yield point. And for the ground motion, I selected 50 records from this user interface, PLNJ records, and we have a previous LAT talk that covers the details, each step, how to use this PLNJ records to select, define a set, define a site location, and pick up a target response spectrum, and select the records to fit the target spectrum. And here I'm just to pick up 50 records to match the ASE 716 design spectrum. And once that's set up, I can just click a Run button to start analysis. But as mentioned before, I would like to include the ground motion intensity measure also in my data structure, or you will see the surrogate model later. So under this advanced option here, you can check on this box here to active this option. So there are several other things for the PLoM training, but specifically would like to focus on today is the user-defined variable, where you can do user-defined script. You submit a script to calculate the intermediate or actual variables from structural responses or other demands in the analysis, or you can use the configure the ground motion intensity. Here I just include the pseudo spectral acceleration at 1 second, which is quite close to the fundamental period of this structure. And another one is the S ratio. It's kind of like a unitless intensity measure to describe the response spectral shape beyond the fundamental period. So I specified the period range for that is 0.2 to 3 seconds. So this, you can imagine that it will be described the average intensity measure, but normalized by the essay at 1 second. And once that's done, I can just click a run button as I showed in the first example. But here, since it's kind of like a 50 records, so it may take some time. So I did a pre-run here. You can also try to download the example, which I will share in the chart file here with the example input file for the 3 examples here. So please feel free to test and try it out. And but once the analysis is done, we will back to this data table again. So you can see now we have all the individual 50 runs, but I generate more samples for the case that we have. So 50 records, but I generate 200 new samples based on the learning process. And for each column here, let me just explain a little bit more of their attributes here. The first one is the pseudo acceleration response vector at 1 second, and in the x direction and in the y direction, 2 horizontal direction of the ground motion, and the SA ratio in x direction and the y direction. And from here, you can just simply click through to see what's the relative influence between influence from the ground motion intensity to the structural response. Let me just so I'm now plotting the PSA at in x direction versus the oops, sorry. Versus the stored floor displacement in just plotting the SA at in y direction versus the peak flow displacement in y-axis in y-axis as well. So in the plot, the axis is the peak flow displacement in y direction. Y-axis is the SA value. So you can see roughly it's kind of like a positively correlated, but with a standard deviation correlation and standard deviation in each direction. And but what you can do is to save this table. For instance, I could do just save the example 2 output, and once that's saved, you can find it out at the place that you have. Save it somewhere else. Let me just save that again. MDOF. Okay, that's under my example MDOF 12, and I have this output file. So let me just open it. So it's the full table that's from the training parts, and you can continue to post-processing this data, but also in the meantime, you can also save this PLoM model, which include more data structures, the entire surrogate information into a local space. I'm just going into the same folder again. And once you save that, you can actually, let me just bring back to space. It will save this surrogate information into a HDF file. Don't worry about this data format because we have the integrated functionality that allow you to load the pre-trained model. For instance, now I want to reload this model back, and everything will be going to loaded from this file to get those training information. And from there, you can continue to generate new samples once you pick up an old model. And for instance, I can pick up another one, which I saved earlier this morning for the spiral data, which is basically those 3-dimensional data structure. And you can continue to generate new sample. And so the first 2 examples just to show a bit of flavor of the how the algorithm could work to learn those nonlinear structures and how to get those responses predicted and include the intensity measure in our training step and automatically. And the last step I want to show you is present to you about in the earthquake response of 12-story building. This is ongoing study we are conducting now to use the PLoM algorithm. So basically, what we have is a 12-story concrete moment frame, and we first run classical multi-stripe analysis, which basically select 100 records per intensity level and runs through the time history analysis to get the peak responses at each story level, drift ratio, acceleration. And if I plot the entire data set, so here, let me just open up a later point. I have this is the scatter data plots for all the first three ground motion intensity measures, AC value, AC ratio, and the ground motion duration of each analysis, and then the story drift ratio, peak story drift ratio, and the peak flow acceleration. And it can be really a larger matrix if I have even a taller building, or I want to know more about the local responses. For instance, I want to know the structural limits controlled by concrete cracking or concrete crash. So I will maybe record the strain value at each story level, get the peak number, and I can pan this table even bigger. So that we put this entire data into the our PLoM algorithm and try to learn the data point, the data structure, and generate new samples to see if that could represent the original data set to describe the structural responses. And on the bottom right figure, I'm just showing the comparison. That's where the gray round dots, the multi-stripe analysis, which are the training data points. And I got the estimated moving media and plus minus 1 standard deviation in the black curves. And for the new PLoM method, we actually train the model and generate a new sample, which are plotted in the squirrel blue dots here in the figure. So you can see it's actually pick up those data structure, but fill in those spaces which naturally see in the multi-stripe analysis. Well, we also estimate the moving media and the plus minus 1 standard deviation. So you can see it's quite close in terms of those different intensity level. Start to get less bounded or controlled at the higher intensity level, close to the boundary of the original data sets, typically not well described here. That's kind of like one limitation that's in this PLoM algorithm, but otherwise all very relatively very good agreement between the PLoM results and the multi-stripe results. And another important aspect, as introduced before by Matt, that we want to really look into the correlation structure. So let me just moving on to the a little bit. The top triangular just plots the correlation coefficient for my story drift ratio and the peak acceleration, directly estimated from my multi-stripe analysis. Well, the bottom triangle actually from our estimation based on the new samples generated by PLoM. So you can see basically it's really pick up the correlation structure well. And on the middle plot, I'm just try to compare two things. One is the summation of the PFA given multi-stripe analysis results, which is in the black curve, and PLoM predicted PLoM new samples results in red curve in agreements. And interesting, just try and error. Use the multi-stripe results to do a resampling, but without correlation between different responses, basically different at different story level. So I got the yellow curve. So you can see if you actually ignore this correlation, it can be a problem sometimes if you go into estimates the damage or loss, because those things are actually based on the correlate or like a correlated realization at different story levels. And the last information that I want to share with you is about the computational efficiency, the computational cost. So here, actually, the original training data from the multi-strap, we have 6 intensity level, 100 records per intensity, so overall 600 nonlinear time history analysis. And it completed by 12 CPUs in parallel using 5 hours. And we scale it up if we want to estimate the responses under 10,000 records. For instance, if we mount the structure in a scenario, different scenarios in original analysis, that's typically maybe we want to see in the future. So the computational time can be dramatically increased by scaling this number of scenarios. So in the y-axis, I'm plotting the job time. Here I just use the linear scale from this 600 time history analysis, but assuming that we're actually running on more CPUs in parallel, 50 CPUs, it still take about 65 hours. But while if we currently using this 600 analysis, while using the same resources, 50 CPU, it can be really completed in 80 minutes. And based on those results, we can get our training going on and estimate the new samples. For instance, now I want to estimate 30 new more like realizations through the PLoM training data. And then just to take less than a minute to generate those new samples. And if you just combine these two, you can see that how much you can save from using this new methods if you're looking into a really big problem like regional analysis. And I think that will end my presentation today with this main slides here. Finally, maybe just to quickly cover a few the coming live expert tips will be Dr. Barbara's Tina on the generating building specific regional level inventories using Braille's, which will be very exciting topic. I'll definitely will also go in there. And others previous live expert tips that will be uploaded in or already uploaded in our YouTube channel. So please feel free to review and play back any of those interested you. And with that said, I want to just end my presentation with this question slides, where you can also submit questions after the session to our SimCenter forum. Thank you.
Kuanshi, thank you very much for the presentation. Those were very interesting examples, required a lot of computation time and a lot of development there for the surrogate method. I don't have any questions for you at this time, and so maybe we can wrap up the recorded portion of today's live expert tips. For those of you in the audience, thank you for joining us. And as a reminder, for those of you who are viewing it online, you can register for other live expert tips and upcoming events at our webpage, which is simcenter.designsafe-ci.org. This concludes today's live expert tips with the NERI SimCenter. Kuanshi, thank you very much for today's presentation. And we hope that those of you in attendance have been inspired to pick up these examples and adapt the capabilities into your own research.